Swayam Prabha. Digital India. Educated India.
So let us continue. You see, you see what we are trying to now do is try to understand this business of signed curvature and signed normal. Okay, so as I was trying to tell you, I was trying to give you last time, this motivation about the need for signed curvature and signed normal from an analytic point of view. Okay, see the recall that the reason why we had to introduce the sign curvature, that is to put a sign on the curvature, is because we had to define the sign normal. And the problem is that if you give me a parameterization of a curve, from the parameterization a tangent direction is always given. Okay, and but then that at every point I know the tangent direction for increasing values of the parameter. Okay, but the normal direction is not uniquely given. Okay, because through a point I can draw a normal line. Okay, but to choose a normal direction I have to choose one of the two opposing directions. So what we had to do is to, in order to have a uniform choice, we define what is called as the sign normal, and that is you take the tangent and then you rotate it by 90 degrees anti-clockwise and you call that as the sign normal. Okay, now the problem with this sign normal is that it creates issues in the formula that you write for the position vector of the center of curvature. Okay, which is essentially the locus of the center of curvature, which is actually going to be the evolute, as we are going to see. But in that formula what happens is that when we take the usual normal, that we consider geometrically is called the geometric normal, and that is a normal that always points towards the center of curvature. Okay, the problem is that sometimes depending on whether the curve is concave or convex, okay, the direction of the geometric normal and the direction of the sign normal can change. Okay, and that is what creates a issue with the sign, and that sign issue is absorbed in the curvature and you call it the sign curvature. So you see this notion of sign curvature is something that is it's an adjustment that we make out of geometry. But the point is that it's not just a matter of putting plus or minus. There's something more to it. There is a whenever you do something geometrically, you want to have that expressed analytically, okay, without using any geometry. So you see, this is part of abstract mathematics. Always we are inspired by geometry, by pictures that you can see. Then the point is you should be able to write out analytic expressions which even without seeing the picture will tell you what will happen in the picture. You see, that's the whole art. Okay, so I want to make sense of the signed curvature, and I want to make sense of the signed normal in an analytic way. I don't want you to look at a picture and think of it. Now, so I want an analytic expression for that. What is the, of course, that I want an analytic expression for that is always important, because that is how you make anything that is geometric into something that's completely mathematical. Okay, but the point is there is more to it. As I told you last time, what happens is that the sign normal and sign curvature, they help in understanding many things. For example, if you take the curve itself as the path traced by a dynamically moving point, okay, then you see the dynamics of this moving point can be given by a differential equation. Okay, and because it's a moving point in on the plane, I can have a frame at every point uh, where it is at every point where it is where that point is being at every point at every instant where that point is being considered. Okay, I can have two directions, and these are the standard frames which consist of the tangent and the unit tangent and the unit sine normal. Okay, and as the point moves on the curve, this also moves. And somehow if you can write a differential equation about how this moves, namely I want to know also the derivatives of the unit tangent and the unit sine normal, okay, and write a differential equation, then the curve will be the solution of that differential equation, and that differential equation turns out to be a matrix differential equation, and believe it or not, the coefficients are, it's a skew symmetric matrix differential equation, and the entries are exactly the non-zero entry is exactly the sine curvature. So that is the importance of analytic importance of the sine curvature, that it completely gives you the differential equation for the curve, the dynamic equation for the curve as a differential equation, as a matrix differential equation, with the matrix being a skew symmetric matrix, and solving that equation gives you the curve. Okay, so it's so in that sense, you see, it is equation of motion of a particle on the curve, moving on the curve or tracing the curve. And for what is essential for that equation of motion is this sine curvature. Okay, so that is, and so this business deals with what is called is as the Frenet-Serret relations or Frenet-Serret differential equation. Okay, so that is one important thing. Then the other thing I told you was trying to understand this business of total curvature. Okay, so I was trying to tell you last time that if you try to calculate the total curvature of as you go around once around a circle, then the total curvature turns out to be this 2 pi. Okay, and because the curvature, if you take the circle of radius r, the curvature is 1 by r, and you have to integrate 1 by r over the arc length. Okay, and 1 by r is a constant, so you get arc length by r, but that's 2 pi r by r, so you get 2 pi, and therefore you are getting the total curvature as 2 pi. Now this is a very general this is a paradigm for a very general thing called the Gauss-Bonnet theorem, which says that total curvature is always a constant. Okay, we are going to see this for curves, for surfaces also. Okay, and it's most spectacular for surfaces. For curves, what is going to happen is that you are going to have a spectacular version called the Hopf's Umlaufsatz, which means Hopf's rotation theorem, which says that if you take a smooth closed curve, simple closed curve, then as you go around the curve, the tangent vector will exactly change by 2 pi plus or minus 2 pi, depending on the way you are traversing the curve. This seems like a very obvious statement, okay, but it's very hard to prove. Okay, and one of the ways of proving it is trying to understand the connection with the sine curvature, and the fact that the fact we are going to see is actually the sine curvature is going to be interpreted as a change in what is called as turning angle. Okay, so that's what I'm going to come to. So this is the motivation for understanding the sine curvature and the sine normal. Okay, so let us get back to this business of trying to get to understand the sine curvature. So see what is happening. See, so if I take so you look at this situation. See, if I have a curve going like this, okay, suppose this is your gamma t, all right, then what is happening is, if I take a point like this, okay, the tangent vector is like this, okay, and the normal vector is, the sine normal is going to be like this, because I have to turn 90 degrees in the anti-clockwise sense. So this will be the sine normal. Okay, and now you see the sine normal is pointing in the towards the center of curvature, because you will see that at this point the circle of curvature will be like this, and the center of curvature will be somewhere here. So this will be Cp, and this will be C of let me just write, let me not put these things, and just say that this is center of curvature, and this is the circle of curvature. And this is the situation where the sine normal is pointing in the right direction, it is in the same direction as a geometric normal, which is pointing towards the center of curvature. Here what happens is that the sign curvature is positive, okay. And let us just reverse the orientation of the curve, the same picture. So take the curve like this. So I am now going like this, okay. And of course, how will you reverse this orientation? See, if this t is varying from A to B, okay, you just make if the parameter is increasing from A to B, where A, B is the parameter interval on which this gamma is defined. Mind you, this gamma is defined by a map like this A, B, it's an open interval on the real line, and this is going into R2. This is how your gamma is defined, alright. And if you want to reverse the orientation, what you have to do is that you have to go from B to A, okay. So you have to make an appropriate change of coordinates, okay, so that this the t varying from A to B should become something else varying from B to A, that can be made, okay. And so for example, if you take something like if you put S, suppose I put something like so it's easy to guess what it is. You have to just put, let me put U is equal to, I think, A plus B minus T, okay. So you see now when you put T equal to B, then U becomes A, and when you put T equal to A, then U becomes B, okay. So you can make a change of variable like this, okay. And what happens is that this will change it will reverse the parameterization. It will in fact what I should say is that it will reverse the orientation, okay. And therefore the same curve will now go in this direction. But now you see what happens. See, if it goes in this direction at this point, you see the tangent direction now has changed. It has become the other. It's got. So suppose I call this as gamma 1. I should not call it the same gamma because I have changed the parameter. So I'll call this as gamma 1. Then now tangent direction becomes opposite, okay. And then now what is the sine normal? I have to rotate by 90 degrees in anticlockwise sense. My sine normal will be like this. This will be the sine normal. And now again you see. But you see this center of curvature and circle of curvature, they have not changed. Still this is the circle of curvature and the center of curvature is here, okay. So what is happening is that you see here what is happening is that your sine normal is pointing away from the geometric normal. Geometric normal always supposed to point towards the center of curvature. So this is a case of negative curvature. Okay. So you see what is happening in the case of the positive curvature and negative curvature. What is really happening is, you see, it's a question of how the tangent is turning, okay, say with respect to a fixed direction. So here you see I can do the following thing. I can take the tangent vector and this is gamma dot, and then I can take, let us say, the x axis or x, let me just say x direction, positive x direction, and then I can take this angle theta. And if you take it like this, in the case of positive curvature, you see what is happening. As you traverse the curve, you see that angle is increasing. You see that the angle is increasing, so you see the theta is increasing, and this theta increasing is going to be captured by the positive curvature, okay. And if you look at this situation, okay, what is going to happen is that as you go like this, okay, your tangent direction is like this, okay, and as you keep moving, do you see that the theta is increasing in the negative? It is becoming increasing negative values, alright. So that means essentially it is decreasing. Therefore here what is happening is theta is decreasing, and you can see that the sine curvature is negative, okay. So if you think for a moment, okay, this should tell you that for an increasing function the derivative is positive, and for a decreasing function the derivative is negative. So this is one thing that should tell you that somehow you should expect the sine curvature to be the derivative of this theta, okay. That is what correlates with this, okay. So if you look at it more seriously, okay, this is also evident in the following way. So this is the idea of what is called a Gauss map. So what happens is that suppose I draw a curve. So let me just say here, suggests that d theta by d s is equal to ks. Okay. So I'm writing it in quotes because I have not I've still not justified things, all right. And you must understand that I have I have put s here. Okay, I have taken the arc length parameterization, and at the back of your mind why I am doing this is because I need a unit speed parameterization whenever I want to talk about anything, and the unit speed parameterization is given by parameter equal to arc length. Okay, so I just want to give some motivation. So now you see, what is this Gauss map? See, the Gauss map is, suppose you are going on a let me take a smooth curve like this. Okay, and what is this Gauss map is, you take the curve to be unit speed. Okay, gamma is equal to gamma of s, unit speed parameterized curve. That means it is a regular curve, and unit speed parameterization with increasing arc length. Okay, mind you, when you do this unit speed parameterization, I told you that you can either use plus arc length or minus arc length plus a constant. Okay, so I want to use plus arc length so that all the signs come out correctly. All right, so you take this kind of a unit speed parameterization, that always exists for a regular curve. That is something that we have already seen. Okay, and what is the so what happens if you give me, suppose I give you a point t naught, okay, or in this case the parameter is s, s, so let me call it as s naught. Okay, if you take the point s naught, let us say this is a point gamma s naught. Okay, at this point I will get a a tangent vector. Now this tangent vector will be gamma dot of s naught. Okay, mind you, it's a unit vector. Mind you, it's unit speed, so gamma dot is always norm 1. So what you do is, you think of something like a speedometer dial with a with a pointer. Okay, if you take the unit circle and put a pointer there, that's a unit vector. Okay, and it wiggles like this, showing you the direction. All right, so what you want to do is, you want to record this this movement of the tangent vector by a pointer on the unit circle. Okay, so basically what you do is, so here is my unit circle. Okay, in R2, this is the unit circle, and then what I do is, you see, now corresponding to this I get this vector here. So this is gamma dot s naught, right? And if I take some other point, let us say, suppose I take some point here. Okay, then I get, suppose this is say s1, this is gamma s1 is the point here, then I get this gamma dot s1. This is again a unit vector, and now you see this unit vector will be like this. So this is going to be gamma dot s1. Okay, now you see, therefore, that in general what is going to happen is that if you give me any point gamma s, I am going to get this gamma dot s, which is going to be a vector like this. Okay, and you see the way this this tangent vector is turning as the curve turns, that is recorded by this pointer on the unit circle. Okay, which is going back and forth. It's recording the direction that the tangent vector is making with the fixed direction, if you want the positive x direction. All right, and the big deal is that this is what is called the Gauss map. Okay, the actual Gauss map was defined for the case of a surface, but then it is a very the philosophy is very general, so you can even define it for a curve in this sense. Okay, and now I want you to understand what is the acceleration of the curve. Acceleration of the curve, at least if you take the magnitude of that, that is going to be the curvature. That is the unsigned curvature. By definition, the unsigned curvature of a curve is, you take a unit speed parameterization of the curve, then measure its acceleration, that's a vector, take its magnitude, that is unsigned curvature. So unsigned curvature, the unsigned curvature is what? It is going to be gamma double dot s, and then you take norm of that. This is your kappa, which is the curvature. Okay, it is the magnitude of the acceleration. But you have to be careful, you should take only the acceleration of a unit speed parameterization. Okay. Now, you see what is gamma double dot s? See, gamma double dot s is nothing but d by ds of gamma dot of s, alright. And this is what is gamma dot s is a tangent vector, it is a unit tangent vector. The tangent vector itself is a unit tangent vector because it is unit speed, and you are only looking at the rate of change of that with respect to s. So, it is actually the rate of change of the tangent vector. Now, you see, for the tangent vector, what is it that changes? The length never changes, it is only the angle that changes. So, what you do is that you try to measure this angle that the tangent vector makes with respect to this angle phi s that it makes with respect to a fixed direction, say positive x axis. Then you should expect that this should be just d phi of s by ds. Okay. This should be given by you expect that this should be it. Okay. If the curvature is the rate of change is acceleration, the magnitude of the acceleration, the curvature should be rate of change of the velocity, but the velocity is a tangent vector. So, you are only measuring the rate of change of the tangent vector, but as far as the tangent vector is concerned, only the angle made by it from the with respect to fixed direction, that is what is changing, length is not changing. So, essentially it should be the change in the angle. Okay. So, I have put a quotes here because there is something here. So, the fact is that I should not write it like this because this is a vector and this is a scalar. Okay. So, there is a vector there that has to come in, okay, and there is a scalar there that has to come in, okay, and guess what, the vector there that's the vector there that is going to come in, which is a unit vector, that is going to be the unit normal, and the scalar that is going to come is the sine curvature, okay, and the sine curvature is exactly this d phi by ds, okay, where phi s is called the turning angle because it is the angle by which the tangent turns with respect to a fixed direction, which we take for example to be the positive x direction. So, this phi s is the turning angle, okay, and the angle made, so it is a signed angle made with respect to a fixed direction, say positive x direction. And the beautiful thing is that what is the correct version of this equation? You will get gamma double dot of s will be nothing but k s into n s hat. This is what you will get. If you want to write it properly as a vector equation, the scalar will be ks, the sine curvature, and this n s hat will be the sine normal, and the sine of that ks that is captured by because the ks is going to be that k of s is going to be nothing but d phi of s by ds. It is going to be the rate at which the turning angle changes. Okay. So, let me just write this correctly. So, it is going to be d phi s by ds. Okay. It is a rate at which the turning angle changes, and the point is that if the turning angle is decreasing, okay, then d phi s by ds will become negative. You get negative curvature, negative sign curvature. If the phi s is increasing, then d phi s by ds will become positive, and you will get ks as positive, and that sign change will adjust with the direction of with the ns hat to give the correct direction, okay, so as to make the geometric normal always point towards the center of curvature. Okay. Now, so the point is that all this is just very suggestive. I just want to suggest to you that you see, if you measure the angle that the tangent vector for a unit speed curve is making with respect to a fixed direction, the rate of change of that angle is the sine curvature. That is the fact. So, what we have to do is we need to actually prove this, but there is a small issue. The issue is with this angle. Okay, angle, the problem, The problem with with angle is, you see, angle as it is, if you just think about it in a very naive sense, okay, around a point, it's discontinuous. That is the problem. Okay, see what happens is, if you go around like this, if I start with, let us say, 0, I go around like this once and come back, it becomes 2 pi. Okay, but you see, if you look at this 0 to 2 pi, okay, there is at the point where it is 0 from above and 2 pi from below, there is a discontinuity, because on the top the values are close to 0, 0 plus, okay, and from below the values are close to 2 pi minus. So you see, the angle function is discontinuous. Okay, in fact, the problem that this angle function is discontinuous is what makes argument, for example, of a complex number discontinuous. And if you have done some complex analysis, you will see that the logarithm of a complex number, if you take, the imaginary part is the argument, and because the imaginary part is discontinuous, what people will do is that they will define the branch of the logarithm by making a slit along the negative real axis, okay, and only then it will become a differentiable or analytic function. So the problem with angle is that it is it's very messy, it's not even continuous. Okay, angle is not continuous. But you see what I am trying to do, I am trying to say that the sine curvature is d phi by ds, where phi is a turning angle. So you see, what does d phi by ds mean? Should mean, you see, it means that this angle should be actually not only continuous, it should be differentiable. I should be able to take a derivative of that, and that should give me the sine curvature. In fact, I want the sine curvature also to be continuous. So that means I want this d phi by ds to be continuous, and that means that my phi should be, the angle should be C1 differentiable. Okay, the turning angle phi should be not only continuous, it should be differentiable, so that I can calculate d phi by ds, and I want that derivative d phi by ds, which is a sine curvature, it's going to be a sine curvature, I want that also to be continuous. So I want the angle to be C1, but our usual sense of angle is not even continuous. So what's the mess about this? Okay, so this is a matter of topology and geometry. It can be resolved, okay, and that's what I'm trying to tell you. But I just want to at the outset say that, you see, what is the what is this business of sine curvature? It is a rate of change of the turning angle. Okay, so now what we are going to do is that, we are going to show that such a turning angle exists, and that turning angle is actually C1, and this formula holds. Okay, so that is the aim of doing all this. All right, and once you have done that, from that it's very easy to get hold of many things. For example, Frenet-Serret equations can be written down, and you can manipulate the tangent and normal and their derivatives very easily. Okay, so again, how do you go about this? So you see, our situation is like this. You want to write, so the idea is like this. You have a curve like this. This is gamma s. This is a unit speed parameterization. Okay, and what you want to do is that you want to look at the tangent vector, and which is going to be a unit vector, and you want to write it, you want to associate to it a turning angle. So how will it be? So I take this point, okay, suppose this is my point gamma s. Okay, so let me just put so here, suppose I want so let me put it as gamma s for that, for the moment, for some value of s. Then at this point I will get this gamma dot s. This is the unit vector, right? And I will take the angle that it makes with, let us say, the positive x direction, and call it as, let me call it as so theta of s. And remember, the issue is I want to show that this as s changes, the point gamma s changes, also the tangent, unit tangent vector gamma dot changes, theta s will also change. I need to show that this theta as a function of s is actually C1. That is the challenge. Okay, and again, let me make a fuss of it. The problem is that in general angle is discontinuous. Okay, so what really saves the situation here? So let me draw a picture. So so this is the Gauss map. So you have this dial here. This is the unit circle in the plane. Okay, and I have this vector this is my gamma dot s, okay, and here is my angle theta s. And mind you, it is a signed angle, so the sense in which you are measuring the angle has to be taken into account, okay, that is important, all right. You measure it from the positive x-axis to the direction of gamma dot, okay, that is the thing. So a sign will come in, all right. Now see, look at this picture. If this picture is correct, okay, this is of course a unit circle. Mind you, norm gamma dot is 1 because it's unit speed, all right. This point has to be what? You should get cos theta s sin theta s. You should get this, all right. You have to get this as cos theta s sin theta s, because that is how you parameterize points on a circle, all right. And then you know, the question is that, you know, this, see, the problem is with this angle being C1, okay, this much you can always write, but the problem is saying that this theta s is first continuously differentiable in S, right, that there exists a first continuously differentiable turning angle is the issue, all right. So what I am going to do is, here I am going to do this as a very general calculus situation. After all I am taking is a unit vector. Gamma dot s is a unit vector which depends on the parameter s. So what I am going to do is, I am just going to take any unit vector which depends continuously on a parameter, and I am saying I am going to show that for that unit vector you have a turning angle. Namely, the natural angle you can associate to it is actually C1, okay. So that is what I am going to do, okay. And as you will see that, you know, it's kind of, in a way it looks easy, but you know, proving the first differentiability and first differentiable continuity of the first derivative, that is the technical part of it. And there is one more thing, in principle, you know, normally if you take the word, if you use angle is not uniquely defined, it's only defined modulo 2 pi, okay. So you see, so therefore the point is that I need to, you know, show that such a turning angle exists, all right, and I want to do it for any unit vector that changes, okay. Oh yeah, so now I recall. See, I was trying to tell you that one issue with angle is that you have discontinuity at a point where you start measuring the angle, okay, because in one direction it will be 0, the other direction it's 2 pi. The other thing is the angle itself is not properly defined. You can add any integer multiple of 2 pi to it and you will still get the same point. See, if you point the argument, for example, of a complex number, you can add 2n pi to it, you are going to get the same point. So there is an ambiguity in defining the angle, that is one issue. So whether it's even, whether you want to, even if you try to define it as a function, there is a problem. But if you try to define it as a function, then there is a problem about continuity at a point where you have to call it as both 0 and 2 pi, if you read mod 2 pi. So that is the issue, okay. So with the, but in spite of all this, turning angle is properly defined, okay. So that's somewhat of a mystery, okay. So what I am going to do is, I am going to do the following thing, existence of a turning angle for a C1 unit vector, okay. So this is what I want to do. So remember, in the situation above, gamma s is unit speed parameterized curve, gamma dot is a unit vector because it's unit speed, okay, and gamma dot is going to be C1 because you see all our curves are C2, right, because we need second derivative for curvature, all our curves are C2, so gamma is C2, that means its derivative is C1, so gamma dot is C1, so gamma dot is a C1 unit vector, and all I am trying to say is that C1 unit vector can be written as cos theta s sin theta s, where theta s is a turning angle. And the important point is, I want to say that turning angle is itself C1, okay, that is the hard part, okay, especially when you are confused about this business that angle itself is kind of discontinuous and it is ambiguously defined up to integer multiple of 2 pi, okay. So what is this? So what we will do is, what is the C1 unit vector? So you take f of t comma g of t, okay, you take this as a C1 unit vector. That means what? It means that you see this, if this t is varying on some interval a b on the real line, okay, and C1 means this f and g are first continuously differentiable, okay. So f is f dash of t, g dash of t exist and are continuous on AB. So that is the assumption, and you are also it's also unit vector. So you see this is a point on the unit circle. So you have ft squared plus gt squared is equal to 1. You have also this. So basically it's this picture of a pointer on the unit circle, okay, where this pointer is your unit vector, and it's changing as the parameter changes, okay. So it is like this. So this is my picture. So I have, this is my unit circle, and I have this guy here. This is ft comma gt, okay. And basically you want to show that there exists a turning angle. That means, so claim is, so this is given to you, okay. The claim is there exists a unique, so even before I say it's unique, let me tell you there is a turning angle, okay. There exists a turning angle theta of t, okay, and the third turning angle, let us say we measure it from the positive x direction, okay, like this, and such that your ft should be cos theta t, gt will be sin of theta t, okay. All this is more or less clear from this picture, because if theta t is this angle, I know this ft is going to be cos theta t and gt is sin theta t, okay. This is all right, okay, because that's how you parameterize points on the unit circle. That's not a big deal. But here's the big deal. The big deal is this theta t as a function of t is C1. That is the big deal, okay, with theta belonging to C1 of AB. That is, that is d theta by dt is continuous on AB. So, not only theta is continuous, is differentiable with respect to t, and the derivative d theta by dt is also continuous. So that's too much, okay. That is a hard part. And what about the uniqueness? This theta t, geometrically when you draw the picture, the angle made with the, let us say, positive x-axis, if you choose to measure it from the positive x-axis, that is kind of unique, okay. If you it is unique assuming that you take the smallest possible angle that you measure, okay. Of course, for the same point I can keep adding 2 pi, multiples of 2 pi, or keep subtracting multiples of 2 pi. I'm going to get the same point, all right. But the big deal is that even this angle is unique if you fix the value at a point, okay. Further, so let me write this further, theta of t is unique if we set theta of t naught equal to theta naught with f of t naught is equal to cos theta naught, and g of t naught is sin theta naught, okay. So this angle, to fix this angle, okay, all you have to do is fix its value at one point. This turning angle, if you fix it at one point, then it is completely fixed. That's how this function is very strongly, correctly defined in a very unique way, okay. And so this is what we have to prove, okay. Now what is going to happen is again this very beautiful thing of looking at the picture, writing down something, and then you try to rewrite everything analytically, and now don't look at the picture, and still everything is correct, okay. So this is the trick. So what you do is, so first see, I don't have anything directly about theta t, except that I can write this ft gt as cos theta t sin theta t. I can write it like that, okay. But mind you, I still don't even know whether theta is continuous. Okay, you expect it is intuitively continuous, but you see, in mathematics, if you say something, you have to prove it. You have to prove theta is continuous. You have to prove it. Okay, and for that matter, even this theta is kind of geometrically defined, because you see, angle, is something, is an angular measure. You say it is measured using geometry. It's not something that you are writing analytically. That's what I want you to understand. I am using pictures, okay, but I am going to completely change this into analytic expressions. So what do you do? See, so here is what happens. See, geometry always gives you some, some intuition. Geometry gives you the intuition for analytic expressions, and then once you have the analytic expression, then you can forget the geometry and write down everything analytically. For example, that's how we got the curvature for a curve. Okay, so it is the same, yoga. So what you do is just look at this. See, you want to show that the derivative of theta exists. See, suppose the derivative of theta exists. Let us do a back calculation. Okay, then how will you find that? So you see, you have f of t is equal to cos theta t, g of t is, let us say, sin theta t. Okay, differentiate it, or if you want, for that matter, you divide, you will get tan of theta t is equal to, gt by ft. Okay, now for the moment assume that theta is differentiable. Okay, then if theta is differentiable, okay, then you do d by dt. What you will get is, here you will get secant squared theta of t into d theta by dt, okay, is equal to, here I will have to apply the quotient rule. So I will get ft squared, okay, and I will get ft into g dot t minus gt into f dot t. Okay, this is what I will get. And from this, but you see, secant squared is 1 plus tan squared, and tan is g by f. So you can write this, see, 1 plus g of t squared by ft squared into d theta by dt is equal to ft g dot t minus gt f dot t by ft squared. Okay, now what I will do is, I will suppress all the t's, and I will simply write it as, this will become f squared plus g squared by f squared into theta dot is equal to f g dot minus g f dot by f squared, and you cancel out this f squared, and you will get this expression that theta dot is f g dot minus g f dot by f squared plus g squared. There is no harm in dividing by f squared plus g squared, because it is 1. You see, f comma g are components of a unit vector. Okay, I have assumed that f comma g is a unit C1 vector. You see, that is the assumption. F squared plus g squared is 1. It's a C1 unit vector. So f squared plus g squared is 1. Therefore, this term vanishes. So you get this, if theta were differentiable, you get that theta dot will be f g dot minus g f dot. Okay, you are getting this expression. Of course, when you are cancelling f squared, you are assuming f is not 0. So assume it. So the idea is that when you try to do something for geometry, okay, you assume the best things. But the trick is that at the end you arrive at something which will again turn upon itself to be the starting point. So you make all these assumptions. Of course, to cancel f on both sides, f should not be 0. I agree. All right. But you see, look at what this geometry has given you. It has given you this formula now. Okay. Now the point about this analytic formula is, you see, it only depends on f and g and their derivatives, which is always given to you. And now once this formula holds, now you know how to define theta. Theta is just integral of theta dot. Okay. So you see, this theta is now, you started from geometry and you have an analytic expression. So you see your theta, so you define theta like this. Okay, to be integral from t naught to t f g dot minus g f dot dt plus theta of t naught. Okay, so you see, now I am making this definition. Okay, now I have forgotten my picture. I am making this definition, and you see, whether my I started with the geometric picture of theta, I got this definition, but once I have this definition I can forget my picture, because this definition is always valid. See, I have told f and g are C1, so f g dot minus g f dot is continuous, and the integral of a continuous function exists. So I am just integrating it, and I am calling that as theta of t. So this is analytically it's perfectly valid, okay. And if everything is correct, this must be the turning angle. What you should appreciate is that this has come from an analytic expression. It is inspired by a picture, but finally it doesn't use anything. It only uses the inspiration from the picture. Okay. Now you see what is the challenge. The challenge is, what is the challenge? You have to show that this theta is first continuously differentiable. Okay. That should be all right. That is because you see it's integral of a continuous function. Okay. And if you know differentiation and integration are inverse processes. So if you differentiate theta, you are supposed to get the integrand. F is C1, f dot will be only continuous, okay, and g is C1, so g dot will only be continuous. So this quantity inside is going to be only continuous, but it is the derivative of theta, because theta is the integral of that, and therefore the derivative of theta is continuous. So theta is C1. So you see the way it is defined, automatically it defines theta for you, and it is already C1. Okay. Now there is a thing. So what is the catch here? The catch is you have to say that if you define theta like this, it agrees with the geometric diagram. Okay. See, the way we got to this theta was from this formula for theta dot, and for that the starting point was f of t was cos theta t and g of t was sin theta t. Okay. Now I am going to reverse and say, given f and g, you define theta like this. It's clear that theta is C1. You have to now prove that f of t is cos theta t and g of t is sin theta t. You are going the other way around now. Okay. That means you are saying this is agreeing with the geometric picture. So we then have to prove okay. So let me write this here. We end up with okay. So you define like this. What do you have to prove? So be very understand this very carefully. I first started with ft is cos theta t, gt is sin theta t, and assume theta t is continuously differentiable, and I got this expression for theta dot. Once this expression, I got this expression for theta dot, it depended only on f and g. Therefore, I use the integral of that to define theta, redefine theta now. And then I want to go back and say this theta defined by this analytic expression is the same geometric theta. That means I have to show that this theta t is f of cos theta t is f of t and sin theta t is g of t. So you have to prove now that f of t is cos of theta t and g of t is sin of theta t. You have to prove this. Okay. Now here is where something interesting is going to happen. You have to, so please don't get confused. This is something that now you have to prove. All right. How will you prove this? So again, you know, the interesting thing is all the time you are looking at the geometric picture, okay, but all the time you are writing it cleverly analytically. Okay. So the geometric thinking is always giving you the inspiration. So you just look at this picture. So this is the unit circle. Okay. There is this vector which is 1, 0. Okay. Then there is this vector which is ft, gt. Okay. And this ft is, you want to show that this is cos theta t and this is sin theta t, where this angle is theta t. You want to show this. Okay. And but you see, if you think about it, this is the same as saying that you take this ft gt vector, rotate it clockwise by theta t, you have to get 1, 0. Okay. So this is the same as proving rotate ft gt clockwise, 1, by theta t, to get 1 comma 0. Okay, it is the same thing, right? Now, how will you write this as so I am transforming these two equations into basically a matrix equation, okay? And what am I doing? So, how will you rotate a vector? Let us think of vectors on the plane also as complex numbers, okay? So, now we are going to have a triple point of view. A point on the plane is having a pair of coordinates. It's also a position vector of that point with respect to the origin. It is also the complex number given by that point, okay? What is the rotation of a complex number by an angle alpha? It is multiplying by e power I alpha, where I is square root of minus 1. So, how will I write this? So, I have to say you take ft plus I gt, iota gt, multiplied by, you see, e power minus I theta t. This has to give 1 comma 0. So, I am writing it in complex notation, where this iota is square root of minus 1, right? And now you know, but what is this? By the de Moivre formula, e power minus I theta t is cos of minus theta t sine of plus I sine of minus theta t. So, this is going to be ft plus I gt, okay, into cos of minus theta t plus I sine of minus theta t is equal to 1 comma 0, okay? And rewrite this, you will get ft cos theta t plus gt sine theta t, and this has to be equal to 1, and you see ft into minus sine theta t plus gt into cos theta t is equal to 0. So we have to prove this. This is what you have to prove effectively, okay? And so if you can write it as a matrix equation, because it will involve the rotation by angle theta, you will get the rotation matrix. So you can also write it like this: cos theta t sine theta t minus sine theta t cos theta t. This is the matrix for rotation by minus theta, okay? This multiplied by acting on ft gt is going to give you 1 comma 0. Okay? You can write it in this matrix form. So this is what I have to prove, okay? Now you see, why am I doing all this jugglery, okay? The point is the following. See, all this is just a seemingly complicated way of trying to prove that ft is cos theta t and gt is sin theta t. It seems to be quite twisted, unnecessarily complicated, but it's not. See, the truth is, this is a function of t and you are trying to show this is equal to 1, and here there is a function of t, you are trying to show it is equal to 0. In both cases, there is a function of t you are trying to show is constant, and that's where calculus helps you. You verify that its derivative is 0, okay? That's why all this work, all this trouble, okay? And you can easily check that the derivative is 0, okay? And the fact that the derivative is 0 comes simply from your definitions, and the fact that f is this f comma g is a unit vector, all right? So therefore what I am going to do is, I am going to call this as, let capital F of t be this expression, f small f t cos theta t plus gt sin theta t, okay? I want to show this is equal to 1, okay? In particular, I want to show it's constant, so I will show its derivative 0. So calculate f dot t. What is the derivative of this? Let's write the derivative. So I will get f dot. So let me just suppress the t's so that it's easier to write it. So let me remove the dot, the t also here, okay, and simply write the dot, and remember that dot is d by dt. So f dot will be, see, if I differentiate this, I will get f dot cos theta, mind you theta is theta t, I am suppressing the t, plus f into derivative of cos theta t will be minus sin theta into theta dot, okay? This is the product rule, plus if I differentiate this, I will get g dot sine theta, okay, plus g constant, derivative of sine theta will be cos theta into theta dot, okay. This is what it is. Now watch, you see what is your theta dot? Our theta dot, there is an expression for theta dot. Here is my expression for theta dot, which was the starting point. That's how I define theta. Okay, when you define theta like this, that is because theta dot was taken like this, and the inspiration for taking theta dot like this was beginning with f of t is cos theta t and g of t is sin theta t. Okay, all right. So theta dot does satisfy this. Even from this definition, if you differentiate, you will see that theta dot satisfies this. So I can replace that. So theta dot is just f g dot minus g f dot. So basically, you know what is this expression? I'll get f dot cos theta, okay, plus f into minus sin theta into theta dot is, what was it? It was f g dot minus g f dot, okay, and then there is so this theta dot I have replaced, plus I will get g dot sin theta, and then here plus I will get a g cos theta, and again a theta dot will be f g dot minus g f dot, okay. So this is one thing I have used, okay. Then I have not used one more thing, which is the fact that f g is a unit vector. So you see f squared plus g squared is 1, differentiate, you will get 2f f dot plus 2g g dot is equal to 1, okay, I am saying is equal to 0. So you will get f dot plus g dot is equal to 0. So the point is that f dot can be replaced by minus g dot, okay. So what you do is, now you see, you just collect cos theta and sin theta terms, okay. So let me do this. Cos theta, watch, there is an f dot here from this term, okay, and in this cos theta term, you see I have a g f g dot plus g f g dot, okay, and then the other term is minus g squared f dot, okay. And what I want you to understand is that you see this g dot, okay, is minus f dot because of what I have written here, okay. And so I want to say that these things will cancel out. So here this g dot you replace with minus f dot, so I will get f dot plus minus f dot into f minus this term is f dot plus f squared f dot, and you see now this and this cancels, this and this cancels, so this term is actually 0, okay. So this is cos theta into 0 plus remaining, the other term will be sin theta, everything inside will be 0. So this is just going to be, so the net effect is that this is going to be 0. So you are going to get f dot is equal to 0, and this means that f is equal to constant. And what is that constant? That is fixed by those initial conditions. You see f of t was, what was our f of t? Our f of t is f small f t cos theta t, small g t sin theta t, okay. Okay, and we have fixed at t equal to t naught, theta to be theta naught, okay, t equal to t naught, theta of t equal to theta naught, and then and f of, so in that case what happens is that you will see that this constant will work out to be 1 because sin squared theta naught plus cos squared theta naught is 1. So you will get f of t is equal to f of t naught is equal to I will get f of t is cos f of t naught is cos theta naught, and g of t naught is equal to sin of theta naught, okay. So remember, so there's a small point of view that you have to understand, that you see, if you want to write unit vector as cos alpha sin alpha, that has got no calculus involved. Basically it's just trigonometry. So this is just writing this f and g at t naught as a unit vector as cos of something and sin of something. Okay, this for a fixed value of t naught. That is something that I am fixing. Okay, that I can do. That is a boundary. That's like an initial condition that I can always fix, and this has got nothing to do with calculus. Okay, any vector with norm 1 can be written as cos alpha sin alpha, and such an alpha can always be found. I am just saying call that alpha as a take any such alpha. So f t naught is a particular value, g t naught is a particular value. It satisfies sum of squares is 1, so it's a point of the circle. So it is cosine and sine of some angle. I am calling that angle as t naught, as theta naught. That I am allowed to do. Okay, and basically at one point I can do it. The fact is, if you do it uniformly, okay, at one point this theta t that I have defined analytically is an angle, but as the point moves, is the point given by cos theta t sin theta t the same as the point given by f t g t as t varies? That's the whole business. You understand? So it's kind of subtle. So you see, this f t naught is going to be 1. Therefore you are getting that, you know, f of t is 1. And if you use the same kind of process, you will see that, you know, you will see immediately that, you know, in the same way, to prove this second part, okay, all I have to do is take the left side and call it as gt, take its derivative, you can show its derivative is 0, and g is g t naught, so gt will become gt naught, and gt naught will be actually 0, because you will get you know, minus cos theta naught sin theta naught plus cos theta naught sin theta naught, it will become 0. So you have proved this pair of equations, but that is equivalent to proving f t is cos theta t, gt is sin theta t, because that's where we started from. So therefore you have proved the existence of a turning angle. Okay, but you see, it's very interesting. You start from a geometric interpretation, then you get an analytic expression, and then you take that analytic expression and go back and verify that it, you know, coincides with the geometry you started with. Okay, and doing this going back and forth is what this whole process, what it has given you. It has given you that the theta, which is an angle, mind you, it is first continuously differentiable, which you don't expect of a normal angular function. Okay, that's what you have to understand technically. All right. So let me say this. I just write this. Similarly, can show you know, g of t, g dot of t equal to 0. This implies g of t is equal to g of t naught is equal to 0, and we are done. Okay. So the moral of the story is that you know, we have gotten this turning angle. Okay, and now once you have this turning angle, you can immediately show as a result of this that the immediate corollary of this is the Frenet-Serret equations. Okay, so I will do that in the next class. So it's an immediate corollary of this. Okay, so let me just write corollary. We get Ks is d phi by ds, where phi of s is a turning angle for gamma dot s, number 1. The other thing is you get corollary, we get the Frenet-Serret equations. Okay, and so we will I will expand on this in the next lecture. Okay, so this is to tell you the importance of you know, sine curvature and sine normal. Okay.